test the microphone.
Camera. Do you need me?
Well, don't leave.
To my desk and get some dry clothes on my desk. I'll check back with you in a minute, all right?
Hello. You can talk.
Rowdy, rowdy, rowdy.
Hi.
Okay. Hello, everyone.
Good.
Okay. So it doesn't seem like it doesn't seem like we're actually going to have a TA today. So so I guess if you have questions, you should send them directly to me, I guess. So yeah. So we'll get started in just a minute. Yeah, oh, and someone is asking if I'm going to share the screen. I'm actually going to like use a physical dry erase board. So yeah. And okay. Yeah, so you should wait. Do people have the option to pin my video for themselves, or do I have to pin it? I don't actually remember. I've been using Google Meet a lot recently, so I've sort of forgotten how Zoom. Oh, okay, yeah. So just pin my video for yourself, and so we're recording. I don't really know how to answer all sorts of technical questions about Zoom. I just hope that you can like, or let me see if this works. Do you all, or am I supposed to click pin video, or sorry, I'm not. Like, do you all see my video, or did I just do that for myself locally? Okay. I hope that works. If people have technical issues, just like let me know. Okay, so I'm about to start. Yes, I'm recording. So, and yeah, as I said before, I don't have a TA, so message all your math questions directly to me. So let me just answer a couple of questions. Today is the geometry bash class. Okay, let's officially get started. So welcome to Math Divulged, the intermediate class. Today I'll be talking about geometry bash. So basically, someone asked, what is bash? Bash is basically when you solve a problem by directly doing a bunch of computations is what you can think of it as. Or like doing in particular, when you solve, and for today's context, it means solving a geometry problem by maybe doing a significant amount of computation or algebra or something. So your TA for the class will also be me. So unless someone else joins, which I don't think is, which I have no indication is going to happen, but if it does, I'll let you know. But for now, just message all your questions directly to me. So let's get started. So let's get started with today's Math Divulged intermediate class. So, and I will note that this is sort of more geared toward Amy level stuff. So I'm just sort of basically going to not talk about in today's class some of the important ways of bashing Olympiad level geometry problems. So I'm basically going to skip over using complex numbers and using, or they may show up I don't think they'll show up very much at all. And I'll also skip over using barycentric coordinates. If you don't know what those are, don't worry about it. Again, I want to maybe more focus on, I'll mainly focus on using trig and using Cartesian coordinates. And so yeah, I may mention complex numbers a bit, but for the full power of these techniques, I think Evan Chen's website has some really good stuff. So if you go to web.evanchen.cc and then look at the handouts, if you want to, do some harder core Olympiad prep, you know, the 2021 USAMO is perhaps in only about 8 months, so you have some time. But anyway, let's focus on more Amy relevant stuff. So and let me just good. And please don't please don't spam my messages. It's really annoying and makes it hard for me to see like legitimate questions. The link to the Discord server should be on our website, mathdivulged.com. So okay, and sorry if this class goes a bit rougher, is a bit rougher than usual today. Okay, so some basic facts about trig that you probably already know. You have the law of sines, which I'll phrase in the form of the extended law of sines, which is that if you have a triangle ABC with circumradius r, so it's a triangle inscribed in a circle of radius r, and then you have its angles A, B, and C, and its side lengths A, B, and C, then you probably already knew this. And so you can use this to convert stuff about angles to ratios of lengths, and maybe with more computations, you know. I won't, you know, without, you know, you can imagine. Another useful thing, and the proof of this is basically just like, I'll just assume the triangle is acute. Basically, you can just like look at this one side. It has length A. This angle is A. So if you take the antipode of point C on the circle, which I will assume, I'm assuming the triangle is going to be acute. You can show it for obtuse triangles if you want to. But since it's acute, and for right triangles, but since it's acute, it will lie on this arc. And so now we will know that these angles are equal since they're, you know, inscribed in the same arc. So this will also equal A. And since this is the antipode, meaning that this is a diameter of the circle, this is a right angle. So the radius, and now the radius of the circle is r. So the diameter is 2r. And now look, we have a right triangle. So this is a right triangle. And now just the definition of sine. Sine A is A over 2r. So we have A over sine A equals 2r. And similarly, you can get, you know, B over sine B. You do the same thing for the other sides and you get the whole thing. B over sine B is 2r. Oh, good. Okay, we have a TA. That's great news. Okay. So, Okay, so Brian Liu is now the TA, so thanks for showing up. So if you have any questions, please message him. Like, please message Brian Liu, co-host. I made him co-host of the meeting. So yeah, so send all your questions to him instead of me. Thank you. Okay. So yeah. Okay, this should hopefully run smoother now. So that's the law of sines. And so you can imagine, and you know, it could be reformulated as like the ratio of the lengths is the ratio of the sine. So, you know, another way you could algebraically manipulate it would be, you know, like you know, etc. And then, you know, do a bunch of manipulations. I don't want to do examples of that right now, but you know, shrug. Anyway, another good example is the law of cosines, which you also probably already know. Which says that in a triangle ABC, when you have this angle A and these two sides, then you have b squared plus c squared minus 2bc cosine A equals a squared. So, yeah, and you can prove this. I mean, I guess you can just prove it using coordinates. Like, if you just like take A at the origin and B at c comma 0 and c at b cosine A comma b sine A, and then just like, then a squared is the distance between these points, which equals this, and then you just do a computation using the fact that sine squared A plus cosine squared A equals 1, and you get that this will be equal to this. So those are some sort of basic facts about a triangle. So notice, you can use the law of sines to sort of relate ratios between lengths. In particular, like if you know two angles of a triangle and one of the side lengths, you can use this, like you can use the law of sines. If you know the angles of a triangle and you know one of its sides, you can get all the sides using the side lengths using the law of sines. You know, and if you know two angles like this, if you know two sides and an angle like this, you can figure out one of two options for this angle in some cases. Again, the law of sines. The law of cosines, you can use to figure out the angles of a triangle if you know all three sides, you know, because if I want to know this angle, I can just say, oh, cosine A, just write it in terms of the side lengths. Alternatively, if you have two sides and the angle between them, you can use the law of cosines to find the third side length. So yeah. And you've maybe seen this before. I don't want to spend too long on that, but you can ask questions if you have questions. Also, there are, you know, trig identities. You probably already know a bunch of trig identities. You know, and if you don't, you should, you know, you might want to learn them for the Amy. And for, you know, other stuff, you know. etc. You know how it goes, probably. And if you don't, you probably want to learn it. I will say that one nice way to remember these identities is to sort of think of it in terms of, Euler's famous formula that for any theta, or for any theta, you can sort of look at like this as a sort of exponential. Now I haven't really, well, where I is the square root of -1, E is the, 2.71828 business. This isn't really rigorously defined, but like the point of Euler's identity is that like, it turns out that this will like give you a sensible definition. And so you can just treat these exponents as if they were normal exponents. And so if you write like, so for example, you could write something like cosine alpha plus beta plus I sine alpha plus beta is this. And then you can just like write it as the product of these two things. Just using the same old, to multiply things to multiply exponents, you add to multiply exponential things, you add the exponents. And then you just multiply the complex numbers together, and then you match up the real and imaginary parts. If you've never seen this before, you should work it out. It's a nice thing. And it's a nice way to remember a bunch of identities. It's a nice way to remember these identities and a bunch of stuff. And of course, if you plug in pi into this, you get the famous expression e to the I pi equals -1. But yeah, so this is a nice way of remembering some trig identities. It can be especially useful if you want to like say, oh, what's sine of 3 theta? Well, you just take this thing and cube it, and then you get what you want. Or you could replace 3 with larger numbers, so you'd still have to do more and more computations. And so yeah, trig identities are a thing. And also, you should be familiar with the basic stuff about a triangle. You probably already know, Heron's formula. If S is the semi-perimeter, the perimeter divided by 2, then the area is this. If the in radius is R, you can write the area as this. If the circumradius is R, the area can also be written as ABC over 4 capital R. Also, if you have 2 sides and the angle between them, you can write the area as just like 1/2 that. And notice that like the relationship between these is related to the extended law of sines. But yeah, you probably already know, a lot of you probably already know this already. If you don't, you'll probably, see it some more as you continue with math. Oh, yeah, to clarify, K denotes the area of the triangle. So yeah, this is a bunch of formulas for the area of a triangle. And there are a bunch of proofs of Heron's formula, including apparently, one that uses complex numbers. You can think about that. I don't want to spend too much time on that right now. So, and we'll see some explicit examples of like Amy problems and stuff. I also want to mention Ptolemy's theorem, which is like, when you have a cyclic quadrilateral, That's a pretty arbitrary quadrilateral, I guess. It basically gives you a relationship between some lengths. It says that the product of the diagonals is the product of one pair of opposite sides plus the product of the other pair of opposite sides. So yeah, and this is a nice result. One nice way to prove this is using inversion, which is another nice, but maybe another nice more advanced geometry thing that maybe I don't want to spend too much time talking about. Like in a nutshell, what you would do is sort of construct 3 more points like B prime, C prime, D prime, or like A B prime is 1 over AB, and similarly, and then these would be collinear. And so then this would just turn into, you'd get a bunch of similar triangles. And then this would just turn into saying that like B prime C prime plus B prime D prime equals, or plus C prime D prime equals B prime D prime. But again, yeah, so you should look up inversion. I don't remember if we're teaching about this much at all. Maybe we're not, but like you should definitely read about that. It's pretty good. It's a nice thing that you'll especially see more of if you do more Olympiads. So you should look that up. Go look that up if you haven't seen that before. You know, look it up after class at some point. But yeah, I don't want to spend too much time on that. So it's sort of beyond this. It's sort of beyond the scope of today's class, if you will, which is a more polite way of saying I'm not going to talk about it much right now. But yeah, so that's Ptolemy's theorem. Also, as sort of an aside, if you have a cyclic quadrilateral and you know only the lengths of the sides and you want to know the lengths of the diagonals, how do you get them? Well, you can have one relation between the diagonals. You get one equation between the diagonals using Ptolemy. And so I want to briefly point out, you can get another equation by writing the area of the quadrilateral in 2 different ways. First, you split it into this triangle and this triangle, and use the formula for the area of a triangle like this. Because if R is the radius of the circle, then the triangles all have the same circumradius, which is really nice. So the area of the triangle is this, I mean, of the quadrilateral is that, but at the same time, you can split it into 2 triangles another way and get it like this. And now you just like factor out you set these equal, the 4R cancels, and you're just left with like AC times AB plus BC plus AD times CD equals BD times AB AD plus BC CD. And so now you have 2 equations, and then you can just like, you can multiply both sides by AC and plug in this, and you get some formula for the diagonal length with some square root in it. So that's sort of another aside. Also, I guess I'll mention briefly that Heron's formula, that square root of s minus a, s minus b, s minus c, is a special case of a formula for the area of a cyclic quadrilateral, which is if you have a cyclic quadrilateral and the semiperimeter is S, then the area is like this, is this. This generalizes even, this is called Brahmagupta's formula. This generalizes even more to the area of a general quadrilateral, even when it isn't cyclic. You can look up like Brett Schneider's formula if you're curious, but that's not something, you know, you can look that up, but after class. Anyway, let's move on. So I told you I was going to talk about trig and I was going to talk about Cartesian coordinates. Well, I've been talking for, you know, a good 20 minutes and haven't talked about Cartesian coordinates basically at all. So let me talk a bit about that. You presume, I imagine most, if not all of you already know, you know, what Cartesian coordinates are. And, you know, you can write the equation of a line in multiple ways. You know, you probably know most of that stuff already. Just a couple of things I ought to mention. One is the Shoelace formula, which is when you have some sort of a geometric figure, like geometric figure, what am I saying? When you have a polygon, and you want to know its area, what you do is you go around the polygon and label its vertex and take the coordinates of the vertices. Then you write them down in order going around the polygon. And when you finish, you write down the first one again. And now what you're going to do is you're going to take the products going this way. So like x2 times y1, x3 times y2, etc., xn times yn minus 1, x1 y times y minus n, and then going the other way. And so this, you know, this looks like, I guess, some shoelaces or something. And I guess maybe that's how it gets the name shoelace. And so now add up all these numbers to get some number on the left and add up the numbers on the right. So then the area of the polygon is half of the absolute value of the difference of the left and the right. And I think you can even interpret that whether the sign is negative or positive. You should be able to interpret that in some way as like whether you label the vertices going counterclockwise or clockwise or something, but you know, I don't plan to get into that right now, I guess. So this might be really confusing if you've never seen it before. So let me do a very simple example. So let's take a very easy polygon. I'll take a rectangle with one vertex at the origin. Let's say it's m by n. So you know the area of this rectangle is mn. What would the shoelace formula tell us? Well, let's write it down. 0, 0, 0, m, n, m. And be sure to go like in order around the polygon. And then you write down the first vertex again. Okay, so doing the shoelaces on the left gives you 0, mn, mn, 0. Doing it on the right, 0 times m is 0, 0 times m is 0, n times 0 is 0, n times 0 is 0. So on the left, I get a sum of 2mn. On the right, I get a sum of 0. So the Shoelace formula says that the area of the rectangle is half of the absolute value of 2mn minus 0, which is indeed mn. You know, I'm assuming mn are positive. And so, yeah, and the area really is mn, so it checks out. So that's an example of the Shoelace formula. So, you know, if you want to just directly compute the area of a triangle or a quadrilateral or a what have you, you can use this formula. Yeah, it should be fine whether the polygon is convex or concave. If the polygon, yeah, convex or concave should be fine. If it were self-intersecting, then you would probably get some weird thing that like counts some regions as positive and some regions as negative with like, you know, signed areas stuff. But yeah, but it should be fine whether it's convex or concave. I don't see why it would fail. So yeah, should be fine convex or concave. As just, you know, be careful if you're trying. Just you probably should avoid self-intersections. So yeah, another thing I want to tell you about with these Cartesian coordinates, which may occasionally be useful, like it has appeared on the Amy at least once or something, is like the formula for the distance from a point to a line. Oh, also someone asked about Pix theorem. Pix theorem is, you should definitely look that up, but like Pix theorem is when you have like when you have a polygon where all the vertices have integer coordinates, and then you like do something where you like count the number of lattice points inside and write down some formula. I mean, if all the vertices of your polygon have integer coordinates, you can use Pix theorem. Pix theorem is true, but like if you're trying to, you know, do a computation with, you know, with algebra, that's not so much. You can actually think of Pix theorem as more of a number theory result or something, but you can look it up. You can look up Pix theorem. It basically tells you that if you have, but this isn't, that isn't as much of like the type of geometry that I would be thinking of, but you can use it if that's your kind of thing, I guess. Shrug. And you should feel free to look it up afterward. Just to briefly tell you what it says, if you have a polygon, a non-self-intersecting polygon, all of whose vertices are lattice points, i.e. all the vertices are integers, and there are I lattice points that lie in the interior and B lattice points that lie on the boundary, then the area is I plus B over 2 minus 1. It's a nice formula, but maybe not the most relevant thing for doing like geometry, but it's nice, but not the most common, maybe. Shrug, but it's a nice theorem. So thanks for your question. But yeah, it's definitely a nice result, and you should look it up if you haven't heard of it. Look it up after that. So yeah, I want to tell you about the distance from a point to a line. If you have a line in this form, and you have some point like VW, then the distance from V to the line would be like this, I believe. And this should, I believe, generalize to, you know, planes in n dimensions. I believe it should. I don't recall the proof off the top of my head, but I believe this should be correct. So yeah. And notice the absolute values. So this is another thing that maybe is occasionally useful. And again, if you get rid of the absolute values, it sort of tells you like which side of the line you're on, I guess. You can imagine what it looks like in a higher number of dimensions. If you have this plane and you have some point v1 to vn or some constants, I suppose then it would look like this. And again, the absolute values, if you got rid of them, it would sort of tell you which side of the plane you're on. But yeah, this is occasionally useful for, computation. Anyway, and there's, more good stuff with Cartesian coordinates. Because, Cartesian coordinates do have sort of a synthetic, as in not bash interpretation. And so sometimes you can like reason geometrically with them by like saying, oh, these distances, and then I'll do some, rotation of the diagram or something. And so you can like do synthetic stuff that way. Maybe we'll see some examples, but yeah. So when you have Cartesian coordinates, remember that you're allowed to treat them in a non-ugly way. And remember that you're allowed to treat them geometrically. I think I should, let's just get right into the example problems now. So let me do an explicit example of using the Shoelace formula. Also, so this will be 2017 AMY 2 problem number 3. And let me briefly look up the answer to make sure I don't tell you the wrong answer. So this will be sort of a very explicit example of doing a computation with the Shoelace theorem using just numbers and just going ahead and doing the calculation. Okay, so here's the problem. A triangle has vertices A, 0, 0, B, 12, 0, and C, 8, 10. So, so then the probability that a randomly chosen point inside the triangle is closer to vertex B than to either A or C is, a fraction. What's the sum of the numerator and the denominator? The standard way that the AMY, takes a fraction and turns it into an integer so that you can bubble it in. So, okay. Before we actually, and of course you don't have to use the Shoelace theorem for this problem, but it's an example of a way you could use Shoelace to do a calculation. So first of all, let's figure out what's going on. To be closer to B than A, it has to be on the right side of this perpendicular bisector. the perpendicular bisector of AB. To be closer to B than C, it has to be, you know, on the right side of this perpendicular bisector. So basically the good region of points is this region. Now notice, this is going to be the circumcenter of the triangle. Notice I'm sort of assuming in this picture that the circumcenter really does lie inside the triangle, but like that is just true. Like it's equivalent to the triangle being acute. And I guess you can just check that it is. Like the side lengths are 12 and square root of 10 squared plus 8 squared is, you know, it's, you can just check that the triangle is acute. Like the condition for a triangle to be acute is that the square of any side length is less than the sum of the squares of the other two, and you can just check that that holds here. So it really is acute. So it's a geometrical fact that the circumcenter really does lie inside the triangle. Alternatively, you could like maybe check it, you explicitly computing more stuff, but I don't want to have to compute too much stuff. Alternatively, you could just eyeball it and say, it looks true. Not, you know, for the Amy, you know, maybe if you're in a hurry, that could work for you. Shrug. Anyway, so let's figure out this point. So it lies, first of all, what is this point O? Well, it lies on the perpendicular bisector of this. So its x coordinate is 6. So if its y coordinate is something called y, then the distance from here to here, which is going to be, you know, y minus 0 squared plus 6 minus 12 squared, has to be the same as the distance from here to here. Plus 6 minus 8 squared is 4. So you get y squared plus 36 equals y squared minus 20y plus 100 plus 4. And you solve this equation, the y squareds cancel, and you get like 20y equals 100 plus 4 minus 36. And you get something. You get y equals 17 over 5, I believe. Yeah, okay. You can, this is 68, and so you get y is 17 over 5. So now, what are the vertices of this quadrilateral? You have 12, 0, then this is the midpoint, which is 6, 0, then this is 6, 17 over 5, and then this is the midpoint of this segment, which is 10, 6, no, 10, 5. Okay, so now we have all our vertices. So let's apply the Shoelace formula. Or I should note, the answer to the problem will be the area of the shaded region divided by the area of the whole triangle. The area of the whole triangle, I'll show you, will be very easy. So let's compute this shaded region. You get 12, 0, 6, 0, 6, 17 over 5, 10, 5, and then you write the first vertex again. And now you get something. What is it? Find out. 0 times 6 is 0. 0 times 6 is 0. 10 times 17 over 5 is 34. 12 times 5 is 60. This gives 94 on the left. On the right, 12 times 0 is 0. 6 times 17 over 5 is 102 over 5. 6 times 5 is 30. 10 times 0 is 0. So over here, I'll just write this as a decimal. This is 20.4. So over here, I get 50.4. And so the area of the shaded region is 1/2 of the absolute value of this, which is 21.8, I believe. And now the area of the whole triangle. You could compute it with Shoelace again, but in this case, it's easier just to use, you know, your basic triangle formulas. The base is 12, the height is 10. So the area of the triangle is 1/2 times 12 times 10, which is 60. So the answer is 21.8 divided by 60, which in Amy format is 109 over 300. So for the Amy problem, the answer is 109 plus 300, which is 409. The end. So that's an example of using Shoelace, I guess. Okay. Let me. Hold on a minute, everyone. Also, okay, someone's question sort of jogged my memory, and now I'm remembering that I should tell you about more stuff. So I had forgotten to mention this, but there's another thing you should know, which I guess I forgot to mention earlier, but I'm remembering now, which I guess I'll just mention in its context of the next problem. So let's just move on right ahead and do this next problem, and I'll mention what is good to know for doing a bunch of bash. So the next problem is 2013 Amy 2 number 13. So okay, in triangle ABC, AC equals BC. And point D is on side BC such that CD is 3 times BD. Let E be the midpoint of AD. So then the problem says, if you know that CE is the square root of 7 and BE equals 3, then what is the area of ABC? Which I'll denote with these square brackets. This is standard notation for area, pretty much, using these brackets. And so this question, I believe, will involve something called Stewart's theorem. I don't actually remember how to. So hang on, let me, so Stewart's theorem tells you, like, when you have a triangle, which I'll label, I guess I'll just label as ABC, but and you have some point, which I'll just label as D, but you can just think of as a generic point. These labels are independent of these labels. Stewart's theorem tells you, basically is a formula for telling you how long this length is. And so it tells you that let this be, the side lengths are B and C, and I guess this is M and this is N. And then the length of this whole side is A. So M plus N equals A. And this, the length of segment AD is D. And so if you want to know the length of AD, in terms of the other stuff, so you can use Stewart's theorem, which I believe tells you that, let me double check I labeled this correctly. Right. So, okay, it tells you that d squared is this. This formula is a bit strange or ugly or something. So one popular way of writing these formula is the somewhat humorous formulation with a slightly weird mnemonic. A man and his dad put a bomb in the sink. It is what it is. So that's Stewart's formula. So yeah. So okay. I don't remember much about how you're actually supposed to do this problem. So let's just dive right in and you get to see some bashing firsthand, I guess. Let's just compute. I looked at some solutions, but I don't really remember all the details. So maybe this is, or this will be maybe somewhat like some solutions I've read, but actually, I guess there are a couple of ways you could do this problem. Ironically, let me show you a couple of ways to do this problem, I guess. I was going to show, I saw some solutions on AOPS using Stewart's theorem, but they maybe were overly ugly. Stewart's theorem is, you know, pretty extreme. It has some nice applications, like in particular, if you want to know the length of a median of a triangle, Stewart's theorem is very nice. You just say like, if this is D, then you can just say like A over 2 using the Stewart's theorem thing. And then you can like cancel some A over 2s, and you're left with like 2D squared equals B squared plus C squared minus A squared over 2. And so that's nice for like a median. And you can compute the length of like the angle bisector this way, because like if you want the angle bisector length, you can use Stewart's theorem on this because you know the lengths by the angle bisector theorem, since it divides this side into this ratio. And then you can compute it, which I'll just tell you the answer that you would get. But I don't actually want to, but now for this problem, maybe there are multiple ways to do it. I think I'll do it a Cartesian coordinate way, actually, not using Stewart's theorem. I think maybe I saw multiple solutions on AOPS, and I imagine one of them must have used Cartesian coordinates because it seems so tractable. So let's do that one. Now notice, when you want to solve a problem with Cartesian coordinates, there are a bunch of different ways you can set it up. And so you want to set it up so that the formulas are as nice as possible. So in this case, a nice simple way to set this up will be if you set the midpoint of AB as the origin. Because now I can get away with just two variables. So I'll call this 0, C, and I'll call this B, 0, and then this will be negative B, 0, because the triangle is isosceles. Okay, so now this point D in this ratio will be 3B over 4, C over 4, because of this. It divides it into 3-to-1 ratio. And so now this midpoint E of AD, you just average the coordinates and you get, I guess you get negative B over 8, comma, C over 8. Okay. And now you compute. CE is negative B over 8 and 7C over 8. So you get this. Let's actually change all the, let's multiply the variable. Let's like replace them with like their things divided by 8. So like let's scale all the stuff. We'll scale this. I'm going to scale the variables. Recompute it with everything like, you know, blown up so that we avoid fractions in the coefficients. So then this just becomes negative B, negative C. So B squared, so this, the distance CE gives you B squared plus 49C squared equals 7. This distance gives you 81B squared plus C squared equals 9. And now I guess you solve this. This looks pretty ugly. I guess you can just do it. Okay. There should be nicer ways to do it, but in this case, you can just do it directly, I guess. So multiply this equation by 49 and you get 81 times 49 is 60, is, you know, 9 squared times 7 squared, 63 squared, that's 3969. And so you would get this. And so you're left with like 3968 V squared is 432. That's so ugly. Hang on, just a second, folks. I'm gonna like double check that I'm not messing up. Yeah, I guess. Oh. Yeah, I miscomputed. So yeah, when you bash, do all your computations correctly. 441 minus 7 is 434. Okay, that's so much better. Okay, now this will be 63 squared minus 1. You can do the algebra. You know how to do algebra. So you end up with like B squared is like 7 over 64. And you get C squared, I guess, is 9 over 64. and so, you know, then you would just get like, so b is √7/8, c is 3/8. And so this point just becomes 0, 3, and this point becomes √7, 0. And so now the area of the triangle, you know, the base is 2√7, the height is 3, so it's 1/2 times 3 times 2√7 is 3√7. And so when the answer is amified, you would add 3 and 7 and get 10, I guess. So that's how you can use Cartesian. I guess you can look at the AOPS thread for this problem to like see how you would do it with Stewart's theorem. But this is one way you could do it. Let me show you an example of, what do I want to do? Let me do, also, oh, someone asked, is this how I would do this on the real test? Mostly, I think, but I would have I would have done this system of equations a bit differently, but I probably I might have done it this way. I don't know. But like this is a like I didn't try this problem like very like much at all without just like looking at the solution or something. But this is one way you could do it. Shrug. But yeah, this is a perfectly reasonable way. This is actually, as coordinate bashes go, this one is pretty good. It's very clean, I guess. You could have done this a nicer way, I think, but that requires some more like algebraic observations. I don't want to get into that too much, but you can think about like it would involve writing like, I'll use like beta and gamma. You could, this is sort of an aside, but you could write it as like, and then I think you could like make a quadratic equation whose roots are 7 and 1/9, and like argue that like beta and gamma would have to be certain ways of like having coefficients of that equation. But mostly like you could like do it that way, I guess. So, to answer a few questions, the problem we did earlier about the distance from B being close, like B being a point being closer to B than to A or C, that was 2017 Amy 2 number 3. This problem is 2013 Amy 2 number 13. Okay, and yes, we are in fact over time. I do want to do a few more examples, but like if you have to go, I understand, you know, people are busy. So, you know, this is being recorded. So if you need to go, but you want to watch it, you know, we will have the recording for you at some point, I guess. So if you have to go, thanks for coming, and see you next time, I guess. And if you can stay, great, keep staying. But don't worry, it's being recorded. So, okay, let's do some more examples. I kind of want to do several examples because some of these examples are pretty instructive. I have so many examples I want to do. There are so many good problems. I should probably have some restraint and not go too long. Here, let me do one how do I pick? There are so many. Here's an example. This one is 2019 Arnold tiebreaker number 1. So the problem is, yeah, and thank you everyone who, came and had to leave. Thank you all for coming, but if you can stay, it might be nice if you do. Okay, so anyway, regular tetrahedra, and this is a 3D geo problem, but like most of the importantness lies in 2 dimensions or something like that. Regular tetrahedra, John, Jane, and Joan have I guess the people at Armel sometimes like to make funny, point names. Have non-overlapping interiors. Compute the tangent of angle HAE. So obviously there's going to be some trigonometry involved. There's literally a trig function in the question. So okay, you should like draw a diagram. This might look really weird, but notice that all 3 of these tetrahedra have J and N as vertices. So you can sort of think of it as like, and so then you can look at the other, so a nice way of looking at these tetrahedra is like J and N plus H and O plus A and E plus O and A. And so you can draw the diagram as like H, or that's not to scale. H, O, A, E, all lying in a plane. And then here you have like point J sticking out of the plane and N under the plane on the opposite side. And so now there are a couple of ways to do it. Let me tell you a way I thought of the problem. Now, you can directly compute some stuff. So one way to think of this problem at this point is that, let's say all the tetrahedra have side length 1, 1, 1, 1. So a way that you can think of it is like this distance, if you think of it, it's twice the altitude of a regular tetrahedron. So to find the altitude of side length 1, like from here to here is the altitude, and this is an altitude. So when you have the base of a regular tetrahedron, you do this. And so when you have the point out of the plane, this will give you √6/3 by Pythag. So this is √6/3, this is √6/3. So this is 2 √6/3. And maybe this isn't a bit of an aside from the like main topic, but this is such, I want to do this problem anyway or something. So, and similarly, this is 2 √6/3. And now, what's this distance? Well, this quadrilateral is cyclic. All of its points lie on a plane, and like they're all the same distance from like the midpoint of Jn, which is the center of their circle. You can, if you think about this, just like picture the diagram and you can see what's going on. Like, so you can apply Ptolemy's theorem. So you get HA times OE, that's 2 √6/3 times 2 √6/3, 8/3, is HO times AE, that's 1, plus OA times HE, that's just HE since OA is 1. So HE is 5/3. And now you're basically done. You have triangle. Now you are, you have a triangle. and you want to know a trig function of one of its angles. So at this point, there are multiple things you could do. One way you can think of it is just to like drop an altitude and then like do some length chasing and do some stuff. But in fitting with today's theme, I guess another way one could solve it would be to just apply the law of cosines. If this angle is alpha, then like 8/3, which is 2√6/3 squared, plus 1 minus twice the product of those is this squared, 25/9. So you just do a calculation. This gives you 8/9 is 4√6/3 cosine alpha. And so cosine alpha is 2/3√6, which is √6/9. So cosine alpha is √6/9. So it's an acute, and it's between 0 and 180. And now it's, you can just see its sine is, since sine squared plus cosine squared is 1, and then the tangent is just the quotient of those, which is 5√2/2. Another way, here's another way you could think about this problem. Instead of doing Ptolemy's theorem, handle this angle more directly. Again, I'll call it alpha, because you can think of it as like the supplement of another angle, beta, or not the, this 180 minus another angle on the opposite side, which would be like 3 times the angle cut out by one of these arcs. So if you call the little angle, I guess, theta, then you can just like do stuff. Like if this little angle is theta, then you know that in this tetrahedron, again, by the same logic as before, so you can compute the trig functions of theta. And now let me show you an interesting way. So tangent of theta is 1/√2, which is √2/2. So now beta is 3 theta, and alpha is 180 minus beta. So tangent of alpha is just negative tangent of beta. So what's tangent of beta? It's just tangent of 3 theta. And so how do you find the tangent of 3 theta? Well, let's do that. You can use the tangent triple angle formula. Well, what's that? Well, if you don't remember it, you can just rederive it. So let's do that. Well, let's do that complex numbers thing from earlier again. Because the point is, when you have like cosine theta plus I sine theta, you could just cube this directly to get like a formula for the cosine of a triple angle, look like cosine 3 theta and sine 3 theta, and then just like do stuff. But if you want to get it more directly, you can notice that this is some real, for a number of theta that's not a multiple of 90 degrees, this is, this number is a multiple of 1 times I tangent theta. And then this number is a multiple, like a real multiple, I should say, some real number, some non-zero real, times this. But we know that this is this cubed. So this cubed 1 plus I tangent theta cubed is some, real multiple of this. So to figure this out, to figure out tangent of 3 theta, just cube this, and then, take the ratio of the imaginary part and the real part. So let's do that. I'll just do it in general. When you have this cubed, it's just like 1 minus 3I tan theta minus 3 tan theta squared minus I tan theta cubed. And so this is 1 minus 3 tan theta squared plus I times negative 3 tan theta minus tan theta cubed. So the tangent of 3 theta is this. Negative 3 tan theta minus tan theta cubed over 1 minus 3 tan theta squared. Okay, now just plug in and you get, tangent of 3 theta, which is tangent of beta, is negative 3 times 1 over root 2 minus tangent 1 over root 2 cubed, 1 over 2 root 2 minus 1 over 3 times tan theta squared, which is 1/2, and you get something. Wait. Oh, sorry, this should be a plus. Okay, yeah. Okay, so this negative sign shouldn't be there. This negative sign shouldn't be there. This negative sign shouldn't be there. Okay, that's better. And so you get minus, it's 5 root 2 over 2, 5 over 2 root 2 over negative 1/2. So 10, and so this reduces to like negative 5 root 2 over 2. And so tan alpha is 180 minus that. So it's 5 root 2 over 2 again, the end. And you know this because like the opposite angles of a cyclic quadrilateral sum to 180 degrees. Okay, that took a while. Let's do another problem. Here, let me do a rather involved example. And if you're wondering about the source of this problem, as I said, it's Armel 2019 tiebreaker number 1. Okay. So let's do another problem. So this problem is also, I do plan to have a handout at some point that you can, that will give you more problems that you can just, just sort of directly bash without thinking. But like, I want to, if you want to just see computations, you can just, do problems. And the handout will have some, and you can, ask me about the handout when it comes out, and ask me about the handout problems. But like, I want to show you, examples that are at least somewhat nice, rather than just compute this, compute that, compute this, compute that, and you're just done without, you just, hit the problem repeat. If the problem solution is mostly just hit problem repeatedly with hammer until problem dies, like you can do that I am not going to add very much or something. So let me show you an interesting, but let me show you this problem. So this is 2016 Amy 2, number 10. So, and this has a useful lemma that will be, I think, that is useful, I think, also in Olympiads. And so it tells you about some length stuff. So, okay, what does this say? Triangle ABC is inscribed. Triangle ABC is inscribed in circle omega. And I'm going to draw point C on top. Normally, normally I draw point A on top of a triangle. But like, when the problem asks you to draw C on top, you do, or something. So points P and Q lie on side A. Points P and Q are on side AB with AP less than AQ. Raise CP and CQ meet omega again at points S and T other than C respectively. So you have this picture. And then the problem gives you a bunch of lengths. AP equals 4, PQ equals 3, QB equals 6, BT equals 5, and AS equals 7. And so the problem asks, what is ST? Okay. So okay, let me show you. So this uses a lemma. So let me tell you about a nice lemma. Say you have a triangle. And again, I'll just call it ABC and take a point X on this side. So this is the so-called ratio lemma. AB over AC times sine BAX over sine CAX for a point on the side BC equals BX over CX. Okay. And actually, I believe, actually this should just, okay, this should just hold for any point on the line. So it doesn't even have, so X can just be any point on the line, you know, you probably want to avoid like strange cases where it like equals B or equals C or something like that. Like assume X does not equal C, but it can be any point on the line. It could be here, or maybe it could be out here or something. And so the proof of the ratio lemma is basically this ratio, BX over CX, it's the area of triangle ABX over the area of triangle ACX. Because they share the same height and because, you know, their bases are in the same line. So since area is base times height over 2, the ratio of the areas is just the ratio of the bases. On the other hand, you can write the area of ABX as AB times AX times sine BAX over 2. And similarly, you can write the other thing as another thing, and then the 2's cancel and the AX's cancel, and you're just left with the ratio lemma. I think you could probably also do this using the law of sines. Like, yeah, if you write like AB over BX equals sine BXA over sine BAX, and write a similar thing for AC over CX, and then like just come and also use the fact that like sine BXA and equals sine CXA, since they're, you know, either equal or supplementary. You should just be able to do some algebra and get the ratio lemma. Okay, so let's apply this lemma to this problem. Okay, what do I want to do here? So I'm going to apply the ratio lemma a bunch. So notice, or actually I'll, okay, let me just directly say, okay, AP over PQ times sine ACP over sine PCQ oops, wait, you all can still hear me, right? Okay, yeah, thank you. Okay, so by ratio lemma, this is, wait, no, sorry, AC over CQ times this ratio of sines equals AP over PQ by the ratio lemma. Okay, but notice that that ratio of sines, it's like the ratio, the sine of an angle on a circle, like you can think of this as the extended law of sines again. Sine ACP, that's ACS. So that's like AS over 2R, where R is the radius of the circle. And similarly, this angle will include ST over 2R, and then the 2R's cancel. So this is just AS over ST. Okay. And some stuff is going to cancel. So we don't want to handle AC and CQ. So let's apply this again. Let's apply the ratio lemma again, because AP over PQ is fine. And then AS over ST is like telling us information about what we want, but we still have this annoying AC over CQ. So let's like do the ratio lemma again, but this time considering point B on side AQ. So again, you get AC over CQ times sine ACB over sine QCB equals AB over QB. And again, the ratio of these sines, sine ACB is AB over 2R, where R is the radius of the circle. And sine QCB is TCB, sine TCB, and that's TB over 2R again. And so again, the 2R's cancel. And so now you can get rid of the AC over CQ. Basically, you can write AC over CQ is AB over QB over AB over TB. Which in fact, in this case, I can write even easier as just TB over QB. Well, actually, I want to keep it in this form for now. And so plugging this in here and then like getting rid of the denominator, you get AB over QB times AS over ST is AP over PQ times AB over TB. Okay, and now you can just solve the problem. Like, you can just cancel the ABs and you can just get like AS times PQ times TB equals AP times QB times ST. And then you just plug in and get what you want. It's like 7 times 3 times 5 equals 4 times 6 times ST. So 105 equals 24 ST. So ST is 35 over 8. So the answer on the AMY would be 35 plus 8 is 43. So yeah, notice another thing. You can sort of think of this as saying like, AS over ST over AB over TB equals AP over PQ over AB over QB. And so if you're familiar with projective geometry, this is sort of saying that like when you take the cross ratio of points A, P, Q, and B, and then project it through C onto the circle, you get the cross ratio of these points. And so if you don't know what that means, don't worry, but you might want to look up like cross ratios. And you might want to read about projective geometry, especially if you want to do like Olympiads, you should learn about projective geometry at some point. And in particular, cross ratios are really nice, but like, you should look that up at some point, but don't worry about it too much, but you might want to learn about it at some point. But don't worry about it. Like if you don't know it, you might want to learn it at some point. But that's sort of, but anyway, let's carry on. I think I'll do, I'll do a couple more examples and then we'll call it a day. So here's an example that shows that you can, yes, I know you wanted a bash class and now you get me showing you a bunch of nice problems, but like this is, because these solutions are comparatively nice as opposed to just, compute everything style stuff, but like, I do want to show this nice example briefly. No, actually, okay, I will show it. Well, yeah, I'll show it briefly. You have a triangle ABC, and then you'd let D be a acute triangle. You let D be the foot from A to BC. You let E be some point on AD. And then you let BE intersect AC at P. No, sorry, wait. Yeah, that's what I want. And CE intersect AB at Q. So the problem is prove that DA bisects angle PDQ. This is known as Blanchette's theorem. Okay, so let's use Cartesian on this. Like, this problem is ready-made for Cartesian coordinates. If you just no, actually, okay. Sorry, this class is going to be too long. Well, it'll probably we'll be over by like 5, like in like or no, I think it should be before then. But like I'm not going to do this right now, but like you can solve this with Cartesian coordinates with like very little calculation. That's an exercise for the reader. It'll be on the handout. Let me just show you. I'll just quickly do a couple of easy problems and then we'll conclude. So here's an easy problem. But yeah, we should be over, I hope before 5, but we'll see. So this is 2013 Amy 2 number 4. which is, okay, you have point A is 1, 0, and point B is 2, 2√3. And then you construct equilateral triangle ABC such that C lies in the first quadrant. So I guess that means it should lie over here. Wait, actually, which one? And so the question is, you take the center of, so basically, what are the coordinates of the center? The problem actually asks, like, you take the product of the coordinates of the center of the triangle, and then, you know, you write it as a fraction, amify it. So, okay, so let's do this problem quickly. So first of all, like, there are 2 points that give you an equilateral triangle. There's this one or this one. That's not an equilateral triangle. That's an equilateral triangle. So, but only one of them will lie in the first quadrant. Right. To be for completeness, notice that this angle, it's like 1 and 2√3. This angle is greater than 60 degrees. Greater than 60 degrees. So this sort of is slanted down, meaning that if I take this point, then this will be like less than 90 degrees if I take the foot of the perpendicular. So, you know, its x coordinate will be less than 1. And so this point over here will have an x coordinate, since this is the midpoint, we'll have an x coordinate of less than 0, and it'll be out of the first quadrant. So we want this point over here. So that's C. So we're just going to do it very directly in a sense, which is that, let's take the midpoint of AB. It's 3/2, √3. Just average the coordinates again. And so what I'm about to do is sort of as I've heard said, this is sort of related to complex numbers, but I want to just sort of show you that you can do this without thinking about complex numbers at all. Basically, to get from here to here, you go over by 1/2 unit horizontally and up by √3 vertically. So going from M to P, since it's an equilateral triangle, you know that this is like MP is 1 over √3 times BM, and it's perpendicular. So, you know, if you have that it's go over by 1/2 and go up by √3, you can just rotate it by 90 degrees. So it's now go down by 1/2 and go right by √3, and then divide by √3. So it's now go down by 1 over 2 √3, and is that right? Go to the right by 1. And so now the x coordinate is 3 over 2 plus 1, which is 5 over 2. And the y coordinate is √3 minus 1 over 2 √3, which is √3 over 6. So 5 √3 over 6. And so you get 25 √3 over 12 is the product of the coordinates. So you get 40, I guess, for the Amy answer. And I guess you could just think of this, I guess some complex number suggestion I have heard from someone I know, you could just think of this even more directly by like B minus M is like 1/2 plus I √3. And then just like multiply this by like negative I over √3. You can work out the details, I guess. Like you would get, it's the same thing, but phrased with complex. It's mostly the same thing, but like phrased with complex numbers. and then you just, add in the stuff. You would get that p minus m is 1 minus 1 over 2 root 3 times I, and then you would add in m would be 3 plus I root 3, and then you get the coordinates of p. You would, if you set it in the complex numbers. Because complex numbers, I guess I should have been more explicit about this, like complex numbers, and maybe a lot of you already know, complex numbers have an interpretation geometrically as like the point xy becomes the complex number x plus iy. And so these have a lot of nice geometric properties, but yeah. And so when you add them, you get this as before. And so this, this is good for Olympiad problems and occasionally for like, and sometimes for the Amy stuff, but this class is already almost 2 hours long. But you can go to Evan Chen's website, and also like there are just good books that treat this at a lower level. I guess maybe AOPS pre-calculus or something, but you should definitely, if you want to like do Olympiads, you can go to web.evanchen.cc and read his complex numbers handout, Evan Chen's complex numbers handout. Okay. Let's do one more problem real fast and then call it a day. So, okay, in equiangular octagon, Caroline, this is, the problem I just showed you was 2013 Amy 2 number 4. This is 2018 Amy 2 number 4. So, okay, you have Caroline, and it looks like this. So, and it says CA equals RO equals LI equals NE equals 2, root 2, and these are all 1. And so now you take another self-intersecting octagon, Cornelia, C-O-R-N-E-L-I-A. And so you wonder, what is the area of these regions? And I guess I'll just leave this as another exercise. I just want to briefly say that I just want to briefly look at a way not to solve this problem, which is to just blithely say, oh, I'm just going to use the Shoelace formula. That'll be fine, right? Let me just use the Shoelace formula on octagon Cornelia, not worrying about the fact that it self-intersects like crazy. Actually, would this work? I doubt it. Hang on. Yeah, I don't. Let's see what you would get, and I think you'll see why it would fail. So all the coordinates are nice, right? You got like 1 0, 2 0, 3 1, 3 2, 2 3, 1 3, 0 2. So if you just throw caution to the wind, what would you get if you just applied Shoelace formula to octagon Cornelia, just blindly applying the theorem? You would get 0 2, 3 2, 2 3, then n is 1 0, e is 0 1, l is 3 1, I is 2 0, a is 1 3, and then back to c is 0 2. Okay, So you get 6, 4, 3, 0, 3, 2, 0, 0 gives you 18. And you get 2, oh no, sorry, 0 times 2 gives you 0, 9, 0, 1, 0, 0, 6, 2. And you get 18. And now Shoelace formula gives you that the answer is 0. Obviously something is wrong. So, and I think what happened would be something like this Shoelace formula did something like, it gave you the area of this, like it counted the area of these regions as positive and then these as negative, and it like all canceled out or something. So, or something like that, or as someone is saying you want to take it by individual pieces. Yeah, you should do a bit more work. I'm going to leave that as an exercise for the reader or something. So yeah, because class is already really long. So yeah, you would take it, you know, as someone is saying, you would do the pieces and do stuff. It's still not a hard problem, but you don't want to do that. Obviously the area is not 0. So, okay. So you can figure out the correct way to solve this problem. But just like, let that be a warning that you don't apply shoelace without thinking. And, as a corollary, make sure that you have your vertices in the correct order when you apply shoelace, or you might get the wrong answer. Or you would have a good chance of getting the wrong answer. So put the vertices in the correct order when you apply shoelace, and then, so yeah. And if you want to learn more about, bashing for Olympiads, again, Evan Chen's website has good stuff about complex numbers and very centric coordinates. And so I guess that wraps up today's class. Visit our website at mathdivulge.com. So I'm Luke Robitaille, teaching for Math Divulged, and thank you all for coming. See you next time. And if you have any questions, you can message me over Discord, I guess. Or just email, like if you have questions about the math. And if you have more general questions, you can email us at, I think our email address is mathdivulged@gmail.com. You should be able to find this contact information on the website, mathdivulged.com. Okay, thank you. So I guess I will end the class now. Thank you all for coming. Thanks especially to Brian Liu for being the TA on, I guess, quite short notice. So thank you all. Thanks to Brian. Thank you all for coming, and bye. Have a good rest of your day. Stay safe, everyone. Bye-bye.